So figuring out how to calculate C from these two guys is tricky. There's no sort of easy way to work out this angle. And so here's what we do. We take the vector A and we break it into components, just like we were talking about earlier. And so this piece here is A sub x, and this piece here is A sub y. And we can write here A sub x is equal to A cosine theta A. And if you remember, A is 10 meters and the cosine of 30 degrees is 0.866, so this is 8.66 meters, right? That's A sub x. Similarly, A sub y is equal to A sine of theta A, that's this guy, and so it's equal to 10 meters times the sine of 30 degrees, which is 5 meters. And so this is 5 meters, and this is 8.66 meters, right? And so anytime I want, I'm free to replace A with the sum of these two vectors, right? Similarly, I can look at B and I can say, look, here's my vector B. If I come straight down here, right, I can draw an x component. I know I've drawn it up in the air, but I'm imagining that my little coordinate system is here. Here's my x component of B, right? And here's my y component of B. And so B sub x is equal to B cosine 60 degrees, which is 5 meters times 0.5. We did this before. This is 2.5 meters. And then B sub y is B sine of 60 degrees, which is 4.33 meters. And so now you can see, if I was gonna draw the components of C, here's my vector C. I would draw a line straight down here. I know this is a little messy, right? So this is CY, and this piece here is CX. And you can see that C sub x is equal to AX plus BX, right? Well, what is that? That's 4.66 meters. Sorry. 8.66 meters plus 2.5 meters, or CX is equal to 11.16 meters. Similarly, CY is equal to AY plus BY, and that's equal to 5 meters plus 4.33 meters, which comes out to 9.33 meters. And so now I have the two components of C, and then I know that C squared, that is, say, the length of this guy, is equal to the square root of CX squared plus CY squared. And if I evaluate that with these two numbers, I get a 14.5 meters. And so I can say, look, it's 14.5 meters. Similarly, I can say, if I want to call this angle here, if I want to call that angle theta C, right, I can say tangent of theta C is equal to CY over CX, so that theta C is equal to the inverse tangent of CY over CX. And if I evaluate that with this number for CY and that number for CX, I get I get 40 degrees. And so I have using the components, the x and y components of B and A, I've made this problem solvable just because I can add the x and y components, the x components together like numbers, and I can add the y components together like numbers, and then I can use the cx and cy, the x components of C, to determine both its magnitude from the Pythagorean theorem and its angle from the inverse tangent. So I'm going to add two vectors, A and B, and I'm going to do it algebraically rather than graphically. Well, I'll kind of do it both ways. And so if I have a coordinate system like this, where this is my x and this is my y-axis, I'm going to draw vector A, which looks like this, and I'll put an angle here. We'll say theta A is 30 degrees. Vector A has a length of 10 meters. Right? Now I'm going to draw vector B. B has an angle theta B is 60 degrees, and B has a length of 5 meters. And so we want to add these two vectors and find out what the result is, right? And so this is kind of tricky. We know what it should look like graphically, because the vector C, to get it, I just draw a line from the tail of A to the tip of B, and I'm going to try to make it a little straighter, but maybe I won't be able to do that. Like that. That's my vector C, which is A plus B. But to get the length of C and its angle is actually pretty tricky. So we have to find a way to do that. Mathematically. And so I'm going to go back to what I said earlier about drawing components for vectors. So I can, there's a special case of adding and subtracting vectors, and that's when the vectors point along the same direction. So for example, if I have a vector A and I have a vector B, and they point in the same direction, if this is like 2 meters and this is like 7 meters or something like that, then to add them, let me try it this way. So the standard way of adding them, if I was going to draw the vector C, I'd say C is A plus B. So here is A and here is B, right? I could technically draw these and indicate that they're vectors, I suppose, right? I would start at the tail of A and go to the tip of B. I draw right next to it just so you can still see those vectors and I'm not writing over them. C is equal to A plus B. And its length is going to be 9, right? Since they go in the same direction, anytime they go in the same direction, they add like scalars. So scalars are just numbers, right? And subtracting isn't much different, right? If I wanted to say A minus B, so if I said C equals A minus B, well, what do? I take the vector A like this, and now I put minus B. So if this is B, then this is minus B, right? Still 2 meters, but now it points this way. And so this is A, and this is minus B. And so again, when I'm adding vectors, I go from the tail of the first vector to the tip of the second vector. And so C equals A minus B, right? And so the magnitude of C would be 5 meters, right? Because it would be 7 minus 2. And so vectors that point along the same line are add-like numbers or add-like scalars, as long as you correctly take into account their sign, right? The way they're pointing, especially when you're subtracting them. This is a very important point because later on, like in the next section, we'll be breaking vectors into components and then adding up those components. So I might have a vector here like, here's my A vector, and I'm going to replace it with its components, what we call AX, horizontal component is X component, and AY. And I might have some other vector B that goes this way, this is B, and I'll replace it with BX plus BY. Oops. Plus BY. And so when I'm doing that, I can very easily add the X components together and very easily add the Y components together because they add like numbers. And so that allows me to simplify the addition of vectors algebraically, and we'll get to that in the next section or so. So here's an example with sort of math with vectors. You fly 32 kilometers, 35 degrees south of west. How far would you have to fly due west and due south to get to the same point? And so we can just draw, here's east, and whoops, let me do this one. Here's west, here's north, and here's south. I kind of know that it's going to be over in this quadrant, right? And so 35 degrees south of west, so this is west, so 35 degrees south of it means that angle there is 35 degrees. And we'll say this is 32 kilometers. And so they're asking us, how far would we have to go this way, then this way? And so if you think about that for a minute, what they're really asking about is the components of this vector. If I call this vector A, then this is AY, and this is AX, right? And since this is a right triangle, because that's what components are, the X component and the Y component are at 90 degrees to each other, then I can say, if this is my theta, cosine of theta is AX over AY. So over A, sorry, right? It's the adjacent over the hypotenuse, and so that means AX is equal to A cosine of theta, which is 32 kilometers times the cosine of 35 degrees, and if you multiply that out, you get 26.2 kilometers. I need to move that over a little bit, right? Because cosine of 32 is cosine of 35 degrees is 0.819. Right. Similarly, I can calculate the Y component, and the Y component is A sine of theta, and that's equal to 32 kilometers times the sine of 35 degrees. And that gives us 18.4 kilometers. And so I would have to travel 26.2 kilometers this way, and 18.4 kilometers south to get to the same spot. That's just a calculation of the components of a vector question. So in this problem, you travel 2 miles, 45 degrees north of east, and 1 mile due east. What is your final position relative to your initial position? So I'll draw this way. Say, use a different colored pen, right? And so this is where, this is my y-axis, and this is my x-axis, and this is my vector A, right? And A equals 2 miles. And this thing, theta A, is 45 degrees. And then after I've done that, right, I go 1 mile this way. And that's B, right? And so what I want to know at this point is what is the vector C? I guess I'll just draw it in black. That goes from here to here. C equals A plus B. Right? And so the way we do these problems, just like we saw earlier, is we find the components, right? So this piece here is A sub x, and this piece here is A sub y, right? And then here is C sub x, and here is C sub y. And notice that C sub y is just equal to A sub y, right? Because B doesn't take it up, since B is horizontal or due east, B doesn't move north or south, and so the vertical extent in my graph of CY is the same as AY. Whereas the horizontal extent of C is the sum of the horizontal extent of A, so AX plus BX. And so I can evaluate these, right? I can say, look, AX is equal to A cosine theta A, which is equal to 2 miles times the cosine of 45 degrees, and that's equal to 1.41 miles if you evaluate it, right? Similarly, AY is A sine theta A, which is 2 miles times the sine of 45 degrees. As it happens, the sine and cosine of 45 degrees is the same, so this is also 1.41 miles. And so that means CY equals CA is 1.41 miles. And CX is AX plus BX. And since BX is just exactly what B is, since the X component of B is just B, because B is only in the X direction, this becomes 1.41 miles plus 1 mile. And so CX is 2.41 miles. Right. And so now I have the X components of C. I have CX is 2.41 miles and CY is 1.41 miles. And so I'm going to erase this and just rewrite those, right? CX equals 2.41 miles and CY is 1.41 miles. Well, the magnitude C is just the square root of CX squared plus CY squared, which is the square root of 2.41 miles squared plus 1.41 miles squared, which is 7.8. So that's the magnitude, and then I can say theta is equal to tan inverse theta C, that is this angle, right? The angle that C makes of CY over CX. Right? Since tan theta is the opposite over the adjacent, theta is the inverse tangent of the opposite over adjacent. So if I take 1.41 divided by 2.41. I get 30.3 degrees. And so that's a vector addition problem. I added a vector going in the at 45 degree angles. It was 45 degrees. It was 2 miles long. A vector that was 1 mile long, pointing horizontally, and I got this vector, which is 2.8 miles long and tilted at 30.3 degrees. So once again, we just break these into components. As it happens, this vector just has a horizontal component and no vertical component. If I wanted to, I could just write by equals 0, because the angle, the vector b points horizontally. And so that means bx was easy to determine. It was just the same length as b. And so we use the components to reconstruct the vector c. That's the general strategy for solving vector addition problems algebraically.